I was not intending to remark on the supposed structures in the bedrock below Khafre's pyramid, but so many people have been asking me about it. I thought I would shed a little light on the matter by looking at it through the geological perspective. So I want you to join me here because there's some pretty amazing things that have played out over the Egyptian environment over the last, say, couple of million years. And we're going to talk about that. And I think some of it's pretty mind blowing. As far as the whole question of the structures under the Khafre Pyramid, I'll say I'm ambivalent. Certainly, it would be exciting if that was real. I will certainly admit right off the bat that that would be very exciting if it was real. However, you know, tipping my hat to Carl Sagan, I've got to agree that extraordinary claims require extraordinary proofs. And so I would definitely be requiring some serious evidence over and above what I've seen so far. And with that in mind, I think what I'm going to do, though, is talk about what could be possible. And I think let's take the number of possibilities here. Um, let's assume that the synthetic aperture radar images are not doctored in any way. It does appear that some kind of a structure exists. But the ambiguity of the images precludes any conclusion as to whether these apparent images or structures are natural or man made. I'm biased towards the natural, and we'll go through some material here, some of the geological studies of Egypt that would seem to suggest the possibility or probability that there would be cavities within the limestone bedrock of the Giza Plateau. So let's start out with some geological context to the question, and then we'll consider what this may suggest. Now, most of the bedrock comprising the Giza Plateau is Eocene limestone from the Eocene period of the geological times table. Now, there's some other, for the geologists, there's some mixed in dolomites, which are also calcium carbonate based rocks. There's some sandstone, not much, but there is some sandstone and marls that are, you might say, thrown in for good measure. But to considerable depths, the mass of the limestone, the mass of the bedrock is limestone. Now, if you know anything about petrology, which is the study of rock composition, you know that carbonate based limestone rocks are soluble in acidic water. And this is one reason why there's so many caves found in limestone terrain. Like if I go up here to the next door states, Tennessee and Kentucky, there's lots of limestone and there's lots and lots of caves. But what we want to look at is the climate over the region of Egypt and its nearest neighbor, Libya, to the west. And in fact, for that matter, the whole Sahara Desert, the whole Sahara Desert region of North Africa. So, numerous studies, and I mean, there's dozens of more than I've read, but I've read plenty enough of those studies to know that the Sahara Desert was not, in fact, has not for long actually been a desert. We don't have to go back too many thousands of years when we get to the point where it isn't a desert. In fact, it's almost lush. And so that's what we're going to talk a little bit about here. I want to introduce some of these studies to you and see what this may imply as far as the question of could there be or could there not be structures under the Giza Plateau and under the pyramid complex. So I'm going to begin by talking about a 2011 report that was published in the Proceedings of the National Academy of Sciences. And in this report, they discussed evidence that the Saharan Desert was not always an obstacle to the dispersal of humans northward, the out of Africa theory that you've probably heard of, that humans moved primarily from the equatorial regions and near the in eastern Africa, near the Great Rift area, and then moved northward and eventually colonized all the way up to the Mediterranean. But the problem is that if people didn't have the means to travel across 1,000 miles of desert, the desert would actually act as an obstacle to the migration of human population. Because for one thing, if it's the kind of desert that it is there now, there's not a whole lot to support life. At least the kind that you would expect would be accessible to a roving band of humans. Um, so in this report, I'm going to quote from it. The authors say that there was five authors, and the title of the paper that I'm going to quote from is "Ancient Watercourses and Biogeography of the Sahara Explain the peopling of the desert." Okay, so what made possible this migration across what is now the vast wasteland of the Sahara Desert was that, quote, during the Holocene humid period. Now, the Holocene, remember, the Holocene is the geological epoch that we're in right now. Goes back, it's dated. The date that is now given in the literature is 11,500 to 11,600 years ago, which is a very interesting date because that is a date of one of the great meltwater pulses and sea level rise events that occurred in the transition from the preceding epoch, the Pleistocene, into the modern epoch, the Holocene. And so it is within the Holocene that essentially the modern story of civilization and the rise of organized societies has taken place. Because if we go back 10,000 years, we see the beginning of organized agriculture. We see a shift from nomadic to sedentary lifestyles. We see the dispersion of languages. Not long after that, we see some of the first urban complexes in the Middle East. Well, it's during this period of time that these authors are referring to that was also the Egyptian humid period. So this is what they say. During the Holocene humid period, the region contained a series of linked lakes, rivers, and inland deltas comprising a large interlinked waterway, channeling water and animals into and across the Sahara, thus facilitating these dispersals. This system was last active in the early Holocene when many species appear to have occupied the entire Sahara Desert, which wasn't a desert. They then go on to say, the Sahara was formerly covered by a dense paleo river network with many channels containing very large alluvial fans. Now, what's an alluvial fan? Well, an alluvial fan, if the water is flowing through a constriction and eroding material, and entraining that material into its water flow, and it's flowing in a confined channel, when it opens, say, into a wider channel or a basin, what happens is the water spreads out, it slows down. As it slows down, it loses its competency to carry sediment, and it begins to dump that sediment. And it builds what are called alluvial fans. Alluvial, meaning deposited by water. That's all that means. And it looks like a fan. It's splayed out. Like oftentimes you'll have a mountain, a narrow mountain canyon opens out onto a wider valley. And there you're going to see these fan-like structures spread out. Well, there's many fan structures that are essentially fossil features. They're not really being created on the same scale now in many mountain environments that they were at another time. The same goes for Egypt. So he says the Sahara was formerly covered by a dense paleo river network with many channels containing very large alluvial fans where rivers divide into multiple branches in an inland area. The Green Sahara also contained numerous closed basins that supported some very large lakes. When these lakes were full, they would have overflowed, thereby linking adjacent catchments. Many fans and lake spillways are located in strategic positions that link waterways across the desert. So, what's being described here is so drastically and dramatically different than what's there now. And the supposition here is that migrating humans found this to be a completely hospitable terrain rather than inhospitable, and probably, in fact, occupied this whole region of North Africa, which is very interesting because now you have to begin to ask the question, well, how did it change so quickly? Which it did, because we're looking at a period that might have lasted from 6,000 to maybe 9 or 10,000 years ago, the humid period. Now, the evidence also shows, as we'll go on to look at here, that that humid period was only like the most recent phase in an alternating environmental context between desert and temperate region. And there have been multiple shifts back and forth, is what the evidence is now suggesting. I am actually having my co-host here somewhere. Maybe he'll jump in. Oh, there he is. Okay.
Howdy.
Howdy,
I've just
John.
been listening.
Yeah, I got so carried away, I forgot that you were there. Sorry, I apologize. I'm actually drinking
Yeah, what is it that you're drinking?
fresh pineapple juice. It's delicious. And hopefully healthy. I've been hoarse this week, as you know.
Yes, sir.
It's much better, but I'm still a bit hoarse.
I hear it. There's something going around.
Yeah, there is, and I caught it. I fought it off successfully, but I've still got some of the dregs of it in my throat. So we're talking here about Egypt, and we're talking about that Egypt has, at least Egypt, Libya, North Africa, that whole belt across there has had some very, very dramatically different environments. And the most recent one basically only came to an end around 6,000 to 5,000 years ago. And it's interesting, and I'm not sure what the connection would be with that transition between that type of environment into the arid environment that it is now, which is then shortly thereafter is the rise of the old kingdom of Egypt. Unless it has something to do with the Nile River. Because once the rest of North Africa dried up and turned into desert, the Nile would have been the lifeline. And the floods continued each year on a very regular annual basis, around just not long after summer solstice, when the floods would come down from the Ethiopian highlands. You had the White Nile and the Blue Nile converging, carrying all of this sediment north to the Mediterranean and dumping that sediment into this canyon. Now, that was interesting. I have something here about,
Yeah, how deep is the Nile Canyon? I'm sure our listeners are going to want to know.
Well, that's where I wanted to go with this.
Because something happened. Something changed.
Yes.
You saw the progress of man. Like you're saying, there's anthropological evidence that things were not always the way they are, contrary to the slow, uniformitarian
correct
system that has been laid out for us by the establishment.
Right. Well, wait till you see what I've got to show you here. When you bringing up in terms of gradualism. So this was something I put together here. I was writing, and I put some of this in the newsletter that went out. People should, if you're not subscribed to the newsletter, get the newsletter, because what I'm talking about here, I've got a whole written presentation about some of the accumulated evidence for these extraordinary landscape changes and environmental and climatic changes. So the Nile River, it's a famous, very long river, but it's a low discharge. You might look up John, what is the annual average discharge of the Nile River? It's not one of the major rivers. It actually is a in terms of big rivers, important rivers, it's low on the scale of volume of water being conveyed, if you want to put it that way. Average annual discharge
is 2,800 cubic meters per second at Aswan.
Okay, 2,800 cubic meters
per second.
Okay, 2,800. Let's see.
It reduces to 150 meters per second when it reaches the Mediterranean.
It reduces. Interesting. Okay. Well, that is probably because a lot of it is being absorbed into the sedimentary column that occupies the canyon, the Nile Canyon. So this is something you have to picture here to get the full understanding of what we're talking about here. I will mention that if you look at maps, and we could actually pull one up here if we wanted, the whole northern Egypt is the Nile Delta, which is exactly what we were just talking about, an alluvial fan. It's spread out, and it has that very fan-like shape to it. And I think I'll go ahead and pull up a map here while we're talking about this. We can refer over here to some maps, and that will be very helpful for people to visualize what we're talking about here. So if we look at the map of the River Nile, we'll see that what I was talking about earlier, the alluvial fan, we'll see that the whole from Cairo north to the Mediterranean, from Cairo up to Alexandria, it's all part of this alluvial fan that you can see right here. If I go over to satellite view, it shows up very clearly. You'll notice that in the midst of all of this brown and barren, you've got this green Nile, right? And then you look at the alluvial fan here, the delta fan of this material, sedimentary material being carried out here, and it builds this fan-like structure. And you'll notice it's all green. And one reason for that is because as the water of the Nile discharges, it saturates in to the unconsolidated alluvium that forms the fan. So it keeps it moist and green. So this is what made the Egyptian civilization possible, was the Nile River. And it's interesting that the rise of the Old Kingdom follows shortly after this great transition from the Green Sahara into the Desert Sahara. Now, as you're looking at this, what you're seeing is in the map, the satellite view that we just looked at, and you saw that the Nile stood out all lush and green, right? Well, what we're looking at is the top of an alluvial column of material that has infilled the Nile Canyon. Now, what is this Nile Canyon? Well, the Nile Canyon is an incision in the limestone bedrock of Giza in that area, at least in the area of the near the Giza Plateau. But it goes, the incision actually goes as far back as south of Aswan. By the time the canyon gets to Cairo, it's 8,000 feet deep. Okay, 8,000 feet deep. This is deeper than a mile. This is deeper than the Grand Canyon by 1,500 feet. If we were able to sweep out, clean out all of the alluvium from the Nile Channel, you're going to be looking at a sheer canyon that's 8,000 feet deep right there. And this canyon is right next to the Giza Plateau.
And we're looking at a 2-kilometer descent into the quote-unquote structure beneath the Khafre Pyramid, as opposed to how deep is the Nile Valley?
8,000 feet. We're taking a little bit of a detour here to tell a story that I think is going to be valuable concerning something that recently happened to me. Oh, and I see I'm being joined by my friend and colleague, Mike Robertson.
Hello, Randall. How are you?
I'm doing very well, thank you.
Well, regarding this little story we're going to tell, we won't take too long. We'll get back to the episode shortly, but I understand you were in a conference recently in Florida, was it?
Correct. Yes, in Florida, the
And
beautiful hotel, the Fiana Hotel, I believe it was. Yes,
excellent. And what something happened there? First of all, how was the conference? But then I understand.
conference was great, and the
Okay.
hotel was awesome. But yeah, everything was good, except I was coming down the stairs, and I think somebody just ahead of me had spilled a little bit of something. Was crowds moving up and down, and I think somebody spilled a little something on one of the treads in front of me, and my foot hit it
Mhm.
and slid out from under me, and I tumbled down 3 or 4 stairs to the bottom.
Whoa!
Uh, I survived, as you can see. Look, I'm still here and I'm intact.
No
I didn't
broken
break any
bones.
bones. No, no broken bones, but I sure banged up my left knee.
Mm.
That was the first thing that hit. My left knee hit that tile floor,
Mm.
and it it was painful. But I had to go. I was actually on my way to do a presentation, so I had to tough it out and go do a presentation
Mm.
with my throbbing left knee. So, anyways, got done with that, and then as the day progressed, my knee began to swell up, and it got quite painful. And I was very relieved to remember that I happened to pack my CBD from the gods salve, and I was really grateful that I had remembered to do that.
Mm.
So that night I put some of the salve on and went to bed. I regularly applied it before I got dressed, and then I put some more on at night before I went to bed. And I must say, though, I've, being in the construction and building industry, I've had many falls and injuries and stuff, and I figured I'm going to be laid up with this for a month. We drove home. I think it was 3 to 4 days later. I continued applying the salve, and I would say within a week, I was getting around pretty good.
Wow!
Yeah,
Wow!
it definitely helped. It most definitely, and so I understand that there's a lot of healing ingredients in that salve that can actually penetrate in
Hmm.
to a to to really alleviate the inflammation that's inside during an injury like that.
Yeah. Yeah. I don't have all of the specifications for. As a matter of fact, we might actually, in later segments, we might actually interview some of the people from the company who make the product, and they can tell some of the details of, of the ingredients and what they do and how they. Because my understanding is more than just a pain relief. There's actually
Mm,
healing. There's
healing.
compounds and other ingredients in there that literally heal as well as pain, relieve pain. And that is one of the reasons it works so fast. One of them I know is comfrey.
Hmm.
And that's a big one. I know that for a fact because anybody can look it up. But comfrey is an ancient name for comfrey is called the bone healer,
Uh-huh. Yeah.
and it gets that name for a reason. But you said now I know you take the Apollo oil as well, like when you
Well, yeah.
road trips. Did you
I
have that
when
with
I
you?
travel, especially, I always bring the oil because it helps relax me, and it helps me to sleep. And I have a tough time sleeping sometimes when I'm on the road and traveling. So every little advantage I can take that's going to help me get that rest and get a good night's sleep. Because particularly like if I'm leading a tour, I got to be on all day, and for me to do that effectively, I have to have a good night's sleep.
Okay.
So I always bring the oil when I travel, and I'm now after this episode, I'm like, okay, I'm always going to have the salve with me too. The Nile is the green part. A lot of Cairo sits on the floor of the Nile Valley, and here you see the edge of the plateau, and you see the pyramid complex. And literally, if you go out here and clean this alluvium out, you'll be on the edge of a canyon that's 8,000 feet deep. So, I mean, you don't picture that, but that is a lot of erosion. Now, how long did that take? Uh, how did it happen? Did it come about that this canyon was created that's, 1,500 feet deeper or whatever than the Grand Canyon? Well, that's an interesting story in itself. And I wasn't really going to go there today too much, but I'll mention it. Around 6 million years ago is the estimated age, the entire Sahara, the entire Mediterranean dried up. Entire Mediterranean dried up. So what is the depth of the Eastern Mediterranean? Could you look that up while we're looking at
Got it.
Eastern Mediterranean depth? And we'll see how that compares to the depth of the Nile Canyon.
16,762 max depth.
Okay. So where the river flows into the Eastern Mediterranean, it wouldn't, of course, be that deep right there. It probably, in fact, is pretty close to 8,000, 9,000 feet deep right there. So whatever the explanation for why the Mediterranean dried up, if that water is gone, now what happens is that will accelerate the downcutting, right? It will massively accelerate the downcutting, because what the water will want to do is it will want to downcut to the base level. The base level is going to be the depth of the floor of the Mediterranean at the point where the Nile flows in, right? So how is it that the entire Mediterranean Sea dried up? I don't know. There's some interesting new evidence coming out on that I haven't really followed up on. But the part that really interests me, though, is the refilling of the Mediterranean in an event called the Zanclean Flood. And apparently, if I go back over here to the Straits of Gibraltar and I zoom in, let's go to this. There was a major breakthrough right here because the Atlantic Ocean was still here, but the Mediterranean was gone. So there was this breakthrough right here, and like 100 million cubic meters per second, I think it was the estimate, poured through here, and it filled the Mediterranean. If you look up Zanclean Flood, Zanclean, the Zanclean Flood. Let's get the exact date on it. I just threw out an approximate date of 6 million years, which I remember from when I first learned about this. The date's probably been refined.
5.33 million.
So it's gotten a little younger, 5.33 million years ago. What does it say about the Zanclean Flood?
It's theorized to have refilled the Mediterranean Sea 5.33 million years ago. The flooding ended the Messinian salinity crisis.
Messinian.
Thank you.
Messinian salinity crisis.
Messinian salinity crisis, and reconnected the Mediterranean Sea to the Atlantic Ocean, although it is possible that even before the flood, there were partial connections to the Atlantic Ocean. The reconnection marks the beginning of the Zanclean Age, which is the name given to the earliest age on the geological timescale of the Pliocene.
That would make sense. So you had this shift in geological epochs that seems to have this defining event. Mm-hmm. Well, what they didn't, did they get into the flood at all? Talking about the magnitude of the flood?
We're looking, sea level rise in the basin may have reached rates at times greater than 10 meters per day.
Okay, think about that. 10 meters per day. That's like 33 feet per day. Can you imagine?
Flash flood warning.
My gosh, can you imagine 33 feet per day? So you're standing on the shore. How far inland would you have to go to get, you'd have to get above 33 feet. You couldn't stop to rest. You'd have to keep moving.
Miles. You'd have to make miles every day.
Yeah, 33 feet. So that's the vertical. But then how does that translate into the
Depends on how long. Yeah, exactly. Yeah. You'd have to look at the shelf, and you'd have to look at everything else that was going on there.
Do they give you the peak estimated discharge through the straits?
See, a maximum of 100 million cubic meters per second.
Okay. I did get that right. 100 million cubic meters per second. Good God. That's 100 million, 100, 1, 2, 3, 4, 5, 6 per second times 35 to convert it to cubic feet, because there's roughly 35 cubic feet in a cubic meter. And I'm going to divide that by 350, 3, 4, 5, 6. So, okay, so that's at least 10 times greater than the Missoula flood peak discharges. At least 10 times. Oh, look at there.
So this is an artist's rendition of it right here.
Aha.
What it might have looked like from the satellite if there'd been a satellite 5 million years ago.
So this is not an actual satellite photograph from 5.3 million years ago?
Yeah, it was lower resolution back then, you know.
Aha, okay. Yeah, okay. So now think about this. We know that the canyon was already there during the refilling because marine waters backwashed into the canyon all the way to Aswan and then deposited marine sediment. So there's thick layers of marine sediments sandwiched in between the freshwater sediments that were carried down from what were undoubtedly extremely vigorous rainfalls, because there is evidence that even that the discharge of the Nile River has been at times much greater than now. What was the number we came up with? You looked up the average annual discharge.
The average, what I pulled up was the average discharge per second, and that.
Oh yeah, right.
That was down at the Mediterranean Sea. We're looking at 103.50 cubic meters per second.
How many?
150 cubic meters.
Okay, 150 cubic meters per second. Okay. And then it was greater at Aswan.
Aswan was 2,800.
2,800. Well, that's a significant difference. 2,800 to 150.
Where's that water going?
Well, it's what's all that green lush stuff. It's turning into soil and percolating into the alluvium. That's what's happening.
Mm-hmm.
So, anyways, let's go on here. So, this is from a standard geological text on the River Nile. It's by a well-known Egyptian geologist by name of Said Rushdie. And it's entitled The Geological Evolution of the River Nile, published in 1981. This is what he says. I'm quoting from his work now, from this book. The Nile is not only small relative to other rivers of the world, but it is also small compared to its predecessors. Since the incision of the valley of the Nile as a Grand Canyon, some 2.5 kilometers deep, about 6 million years ago, okay, this is where I got the 6 million years from, gigantic rivers have come and gone filling this canyon. 2.5, end of quote, 2.5 kilometers is equal to 8,200 feet or 1.5 miles. It took an extraordinary amount of water to carve a canyon to this depth. And this canyon, as I said, sits right on the edge of the Giza Plateau. Now, does that have any implications as far as the question of what might be under the, I don't know. But let's go on. The whole area of the Sinai Desert, south of Egypt, let's talk about a little bit about that. This is from a paper that was published in 2009. It was actually presented at the fall meeting of the American Geophysical Union. Title of the paper is Mega Floods and Landscape Change During Oxygen Isotope Stage 3 in the Sinai Mountains. Oxygen Isotope Stage 3, we'll talk about that in a second here. So this 2009 fall meeting of the American Geophysical Union, this is quoted from that. by the way, let's see, oxygen isotope stage 3 stands, it was a climatic period that lasted from about 60,000 to about 26,000 years ago. Interestingly, note that 26,000 because that's right there at the one full precessional cycle, 26,000 years. And something happened there that caused them to go from oxygen isotope stage 3 to oxygen isotope stage 2. We'll not talk about that here, but that'll be one of the things that we regularly come back to. So we'll be discussing that in more detail later on. What they're also referred to as marine isotope stages, and we'll talk about that. It's because they are marking major rapid abrupt shifts in climate, basically, that define these different stages. Like we're in stage 1, we can go back to stage, I forget, 12, 14, 15, which is couple of 100,000 years ago. So this is quoting now from this paper that was presented at the fall meeting of the American Geophysical Union. Quote, much of the Sinai, okay, here we go. Much of the Sinai is deeply dissected by river valleys or wadis. Within the deeply incised valleys, mighty sediment fillings up to 50 meters are characteristic elements of the landscape's morphology. Reaching the mountain rim, the sedimentation processes formed mighty and broad alluvial rivers. I'll read that again. Reaching the mountain rim from the sedimentation processes formed mighty and broad alluvial fans. So this is what I was talking about earlier. When you have, again, a channelized flow exiting from the mountain front out onto a valley floor or an open plain or a basin, that's when you get these broad alluvial fans. Okay, so what they're saying there, and this is by 1981, when some of the first radar images coming is showing up because of the space shuttle overflights, and they're seeing for the first time what's under some of the sand of the deserts. But a lot of it, as I'm about to show you here in a few minutes, was actually not buried. You can see the large canyons, the large channels, these dissected river valleys, which are called wadis. Okay, so let's see, in the early 1980s, okay, when the North African overflights of the space shuttle was carrying this spaceborne imaging radar, SIR radar, spaceborne imaging radar, and also this system called the Global Land-Based Elevation Project Digital Elevation Models. I'll say that again, Global Land-Based Elevation Project Digital Elevation Models. So using this technology, the shuttle was able to see what lay hidden beneath the desert sands. And what did they see? Quote, both large flood features and later superimposed drainage channels of variable morphology, all drain northeast and east-northeast from northwest Sudan. Some of these channels were enormous. The authors describe alluvium-filled basins or valleys about 100 kilometers in length. This is about 60 miles, greater than 15 kilometers wide, and at least several hundred meters deep. So several hundred meters could be 200, 300. Let's say it's 250 meters. Then we're talking about channels that are 800 feet deep. If we're talking about a channel here, 60 miles long, right? About 9 miles wide and 800 feet deep. Well, if you've been watching or know a lot about the other research on the scablands, the channel scablands of eastern Washington, I could almost be describing one of the great coulees that are about 800 feet deep. Grand Coulee only ranges from about a mile wide to 5 miles wide, right in there. We're talking here, what they said, about 8 or 9 miles wide. but still we're kind of in that same magnitude range, that same ballpark as some of the great coulees that we see in the channel scablands of eastern Washington. And we know that those channels were cut out by floods that ranged in the hundreds of millions of cubic feet per second. Now, is that the same magnitude of flows we're talking about here? Well, we don't know, but clearly we're seeing these channels deeply incised into what is now desert floor with essentially very little or any running water at all. But clearly, this was the handiwork of enormous volumes of water. Okay. Let's see. Yes. So we had both large flood features and later superimposed drainage channels of variable morphology. And where are they draining? They're all draining towards the north, northeast, east, northeast, in the direction of Egypt and Libya. Let's see. So this was from a report that was published in the year 2000 entitled Use of Radar Data to Delineate Paleo Drainage Flow Directions in the Salima Sand Sheet, Eastern Sahara. And this was published in the journal Photogrammetric Engineering and Remote Sensing. So here it goes on. It seems easier to relate landforms in many deserts. This is from, we're getting now into some of the older things, some of the older evidence that I like to go back to, actually even from the 60s. And this is from one of the standard textbooks of the early days of geomorphological studies. And a geomorphological study is essentially the study of the landform. So this is going back to a standard textbook, 1960, right? So even back as far back as 1960, it was already by that time becoming apparent to geologists that water had played a very important and profound role in sculpting the landscapes of Egypt, even though those landscapes now are some of the driest on Earth. All right, so this was from I'm going to quote from a 1960 standard textbook in geomorphology by considered one of the esteemed names within mid-century geomorphological studies. Geomorphology, again, to remind you, is the study of landscapes and landscape formation. This was by B.W. Sparks. So even back in 1960, the geologists and geomorphologists that had been studying the area of the Sahara knew that it had once supported a drastically different climate. So here we go. We're going to quote from that 1960 textbook. Although stream floods and sheet floods may be effective agents in the formation of semi-arid landforms, many deserts bear the imprint of even more significant water action. It seems very doubtful whether the required amount of water ever falls in present conditions, and many authorities have attributed such erosion to a wetter period during the Pleistocene. For example, the valley on the west side of the Nile at Luxor, containing the tombs of the kings, appears to be a water-eroded valley. But the tombs themselves show no signs of destructive water action. This means that water action of any significance probably ceased at least 4,000 years ago. It seems easier to relate landforms in many deserts to earlier, wetter periods than to present conditions. Hume gives photograph after photograph of steep-sided valleys in limestone and sandstone country in Egypt, which are obviously of water-cut form. And now here's, I think, the significant point. Many of them containing caves, from which springs probably issued at an earlier period. The same author has also many illustrations of closely spaced Badlands type of valley pattern on impervious igneous and metamorphic rocks in the same region. Indeed, the chief impression on viewing the Mount St. Sinai Massif from the Gulf of Suez is of the gashed sides of this stark mountain mass. So the point here is that even back in 1960, they were already recognizing that this had to have been a massively water sculpted landscape in these regions, which of course then implies a very different kind of environment. Let's see what else that he has to say here. Yeah. This is what he says in addition to that, in reference to the wadis, which are these water cut. While you're at it, John, and while I'm reading this, why don't you look up wadi, and we'll give the definition, the technical definition of a wadi, W-A-D-I. So B.W. Sparks goes on to say, further evidence for a wetter climate is to be found in the wadi pattern present in many parts of the deserts. These wadis are too long and in many cases form too integrated a pattern for them to have been formed under present climatic conditions. In Arabia, wadis of very great length are known, while some of the patterns in the Sahara have been described. The Hagar Massif was apparently one of the chief watersheds, for enormous wadis radiate from it in all directions. The comparatively recent date at which water flowed in these wadis is attested by the presence of some of the oases of fish from tropical Africa. And then I'm going to defer now here. I'm going to go over to an article which appeared in 2010 in the journal Global and Planetary Change. And the title, this was three authors, Alan E. Kehew, who has done a lot of work in the Midwestern North American floods. He's a very prominent paleohydrologist who has studied some of the great meltwater floods of the Midwestern region, particularly in North and South Dakota, in that area, where a lot of these great spillways have incised big valleys into the prairie. So the title of this article that appeared in Global and Planetary Change is Reconstructing an Extreme Flood from Boulder Transport. Reconstructing an extreme flood from boulder transport and rainfall runoff modeling. This is the Wadi Isla, South Sinai, Egypt. So boulder transport, right? The idea is that the bigger the flood, the faster it's moving, the more powerful it is, the bigger boulders, the bigger rocks it's going to be able to move, transport, and deposit, right? We're going to look at a study now that was presented in the journal Global and Planetary Change in 2010. The title of this paper is Reconstructing an Extreme Flood from Boulder Transport and Rainfall Runoff Modeling, Wadi Isla, South Sinai, Egypt. So we found out, did you find out what a wadi was?
Sure. So a wadi is defined as a valley or a ravine that's been carved out by, just regular water flow, but it's typically dry unless
Correct.
it's the monsoon season.
It will flow and become active.
Correct. Something, and just real quick, it looks something like this. See if I can add this to the stage.
Okay.
Real quick.
Yeah.
So that's a typical wadi in Egypt.
Mm-hmm. This is the area in question. This is the Sinai Massif here. Here's the Gulf of Suez. Now, Giza's up in here. You don't see it off of this picture, but this study is very representative of many of these wadis that do not have major water flow in them now, okay? So let's take a look here. This is the area. This is the watershed that feeds the wadi that you see right here. So this study, we're basically looking at where the Wadi Canyon or ravine opens out onto the plain here. And there's a very interesting deposits there, as you're about to see, that provide testimony that the modern water flows are insignificant compared to the ancient water flows. So this is at the mouth, right? So as that water rushing through this ravine opens into the valley, boom, this is the kind of stuff this is the kind of stuff that it's dumping down right now. So let's look at the next one. So that's a pretty good sized rock. That's probably 1,500 tons right there, 1,000 tons. So that's a pretty major water flow. And we'll just go through some of these. In this one, you see here smaller rocks. So this had been farther from the valley mouth, right? Because the larger the boulders, the bigger the shorter the distance that they were transported. So in other words, as that water spreads out, from the confinement of a channel, then the larger stuff goes down first, and the further out you get from the discharge point, the smaller it'll get. So you see some intermediate size stuff, but this is still a very impressive depositional feature right here. This dashed line shows the level of the water that deposited these boulders here. So he's standing in the wadi here next to these large boulders, right? And in the background, you see the walls of the wadi. There would be another wall you wouldn't see, like this man, the gentleman here is facing in this channel. So the thing here is you can see over here, you see the row of boulders up against the base of the cliff. Well, so the boulders and the cliff are basically the function of the same water flow. So the water flow that carved the cliff quarried out all these boulders and dumped it. Now we can come completely around the other side of the world to the Snake River Plain, and we've got this. And it's the same thing. It's called a coulee, or in this case, it's actually the Snake River Plain. So it's not a coulee, because a coulee would be dry. In North American nomenclature, a wadi would be a coulee, because a coulee is a channel. It oftentimes has big boulders in it and little to no or insignificant water flow. So here you see this is mostly basalt, rounded basalts, and this is the Snake River Canyon, and the cutting of the canyon is what produced this right here. And this here shows a section of deposits. And the interesting thing I like to point out to people, this is a paleo current indicator. A paleo current indicator will give you a flow direction. And the way to understand that, let's see if I got some books handy here. If you have, I'll use think of a stack of books. And if I push them this way, they tilt this way. If I push them the other way, they'll tilt like this. This is essentially what we're seeing in this image. Let's go like this. I want to get the same orientation. I think, yeah, it's backwards, isn't it? So I'm dealing with a mirror here. But yeah, so this would be what you're looking at essentially right here. This is imbrication. And it's a very useful tool for instantly being able to decipher which way water is flowing in a fossil deposit. If that makes sense.
100%.
And this is just a large mass of alluvium. So in the channels, you will have places like in the bends and some of maybe the hollows and stuff, you will have this deposition of more almost like muddy stuff. But if you look in here, like look up at the top, huge boulder up here. Boulders at the bottom, hoodoos forming on the sides, and that's from runoff. Right after this is deposited and you have this clearing out, imagine you've got a thick layer of mud, but the flow continues to come through and it leaves this channel within the mud. the mud starts to harden, but then you have erosion from it, the water subsequent to the deposition of the mud. It dries out. It forms this kind of a deposit right here. And you see right up here at the top, also there's boulders at the top. So this is in the wadi, right? And if we come over to America, all right, so here we have Afton Canyon, which is in the Mojave Desert of California. And this is essentially the same type of depositional feature that we were just looking at in the Wadi in the Sinai Desert, but this is in the Mojave Desert. Let's see if I've got, yeah, so this gives you, see the little guy down here for scale. So this kind of gives you a sense of this. Now, what this represents is a channel that was cut that ultimately leads across the Mojave Desert and terminates in Death Valley. So there was a whole succession of lake basins and interconnected channels that at some point, maybe even around the same time that these wadis were being cut in Egypt, these channels in the western, southwestern deserts formed as well. And just like, you know, you have the same thing. If you start looking, I don't know if you see any big boulders here, but there are large boulders dispersed through this. You also see the formation of the hoodoos here. Essentially, it's the same feature. So what I'm showing you here is we can identify these geomorphic after effects of these gigantic water flows. And once you begin to understand the basic vocabulary or the basic alphabet of these events, you can start connecting these dots and realize that, well, wait a second, we can see that here we have deserts of the southwestern United States that have very similar type of evidence of gigantic water flows, of previous temperate, if even almost lush, when there was rivers and lakes in abundance, and they're gone now. And desert aridification has set in. So to me, this raises very interesting questions about climate and environment and how much it changes and on what scale, on what level. And I think we could say sometimes it changes very fast, very dramatically, and on a perhaps global scale. And this is what tends to be overlooked in a lot of the concern about climate change, to not necessarily try to bring it back to that whole issue, but I'm afraid we need to, because that is kind of an issue in that there has been a very concerted effort to focus the emphasis on one mode of change and one only, and that's anthropogenic, when clearly this kind of evidence is something on a completely different scale. Okay, so this is the configuration of the Laurentide ice sheet lobes in Wisconsin at the end of the last ice age, showing locations of tunnel channels and drumlin topography. Approximately 70 tunnel valleys intersect the margin of the Green Bay, Wisconsin Valley and Chippewa lobes. So here's the lobe. This is Lake Michigan. Here's the state of Wisconsin. Now, if we look at this, each one of these little hash marks represents a tunnel valley. Well, these tunnel valleys are essentially just another name. If they were over there in the Sinai, we'd be calling them wadis. If they were out there in the Pacific Northwest, we'd be calling them coulees, right? But here they're being called tunnel valleys. But like it says, there's approximately 70 of them. And at each of these points, that is where major channels of meltwater coming from under the ice sheet discharged, right? So you have this for one thing, you have this alteration in pressure regimes, but you also, because of that, when it's flowing under the ice, it's under pressure. Because it's under pressure, it's more hydraulically energetic. So it's capable of entraining and moving sediment more effectively than once it discharges from the ice sheet and begins to, it essentially does the same thing. When it's under the ice sheet, it's in a confined channel. It comes out from underneath the ice sheet and it spreads out. So then what it does is it deposits the sedimentary load that it was carrying. So if we go to the next slide, this is, I was able to find like at the Antigo one here in the Bryant, we've got some photographs of the discharge, and it's actually being quarried, and this is what it looks like. So here you see the tunnel valley comes out, discharges from under where the glacier was, and you can see, for scale, look at the dump truck here. Now, go back to here and imagine that you've essentially got similar stuff in every one of these. Oops. So notice the parallels between what we're seeing right here and the pictures of the wadis that we just saw. So all in all, what we're seeing here is evidence of gigantic floods. Now, is this necessarily the same kind of a flood as we saw in the Sinai? Well, not necessarily, because this is glacial meltwater. What was the source of the water in the Sinai? What was the source of the water that was creating the plexus of interconnected channels all over the bedrock of the Sahara? Well, I'm guessing it was probably rainfall. A lot of rainfall. Lots and lots of rainfall. And, but how much rainfall? I don't know. We need to, I'm sure there are more studies because I have not availed myself of all the studies. Probably somebody has done a quantitative analysis somewhere along the line. I haven't seen it, but it would certainly be worthwhile to address that question of where is the source of the water? And if it is rainfall, because I don't think it would have been glacial melt, even during the Ice Age, there was not, like some of the higher mountains like Kilimanjaro and others, yes, did have expanded glaciers, but would that have been enough water source to create the wadis? I don't know the answer to that, but it's a very interesting and important question. So yeah, here's a good overall view. And what's interesting about this is the colors are based on elevation, not vegetation. But this whole area up here, which is now desert, was intermittently green. And there's been a lot of interesting studies about what was happening culturally, what kind of animals were living there. When you look at the floor of the Mediterranean, you can see here that would have been a whole complex. Now, 6 million years ago, again, or 5.3 million years ago, this was all dry. And when that water gushed through the aperture here, we learned that some of the estimates say up to 30 feet per day.
30 feet per day.
30 feet per day. I'm still trying to wrap my head around that. This is from paleoceanography of the post-glacial Eastern Mediterranean, was in Nature, 1979. During the late deep water, the hydrography of the Eastern Mediterranean underwent severe changes in response to climatic fluctuations. Among the most striking of these changes were periods of deep water stagnation. Well, that is evidence that there were after the refilling of the Mediterranean, there continued to be really gigantic floods coming down the Nile. And those floods discharged out with fresh water. The fresh water is less dense than the salt water of the Mediterranean, right? Well, what happens is it forms a freshwater lid that interrupts the circulation, the oxygen circulation that occurs, the thermohaline circulation. It creates a density stratification that inhibits the carrying of oxygen down to deep waters. So what happens, there's not enough oxygen to cause the decay of organic material that is now being flushed out in these very vigorous floods. So the vigorous floods do two things. They flush out organic material that settles to the bottom, and then they create this density stratification that prohibits oxygen from reaching that freshly deposited organic material. So what it does is it doesn't fully decay. It forms layers of sapropel, it's called. Episodes of oxygen depletion are indicated by the presence of layers of dark sapropelitic muds enriched in organic carbon, devoid of the remains of benthic organisms, bottom-dwelling organisms. That's benthic. Several theories have been proposed to explain the past stagnations. They all use a mechanism which stabilizes the water column by forming a steep density gradient in the upper waters. In this way, the vertical mixing and hence the ventilation are retarded, oxygen is depleted in the deep water, and stagnation commences. Olison's theory, whereby influx of fresh water leads to reduced surface density and the interruption of normal vertical circulation, is the most widely accepted at the present. That's still pretty much the same idea. But what this is showing is there was increased precipitation at the same time as these sapropylitic layers were being deposited. We're not going to get into this a lot right now, other than I think that we're going to leave it here at this, and then come back to the question that we opened this discussion with. But the evidence of these sapropylitic layers suggests that there were extraordinary floods coming down the Nile. Extraordinary floods, much larger than any that we've seen in recent years. And notice the date, roughly in that window, right. Here's a good place to leave it here with this and then circle back. The geomorphic evolution of the Nile Valley until the late Middle Pleistocene was dominated by local hydrographic dynamism, with major wadis supplying the bulk of the runoff and sediment redistribution by the Nile. Some 5 or 6 meters of well-rounded cobble conglomerates may overlie the potholed bedrock floors of Nubian wadis. That's another important indication. Potholes are formed by extremely turbulent vortices in fast-moving water. And we don't find a lot of that occurring today.
No.
At all, really. So they imply a local base level at or below modern floodplain and record a last episode of high wadi competence in valleys now transporting little coarser than sand grain particles. So that's obviously a very dramatically different flow regime. And this speaks of major pluvial events in recent geological history of this planet. Very interesting stuff. So we're not going to go there. But then, so here's the thing. All this water flowing over and eroding limestone bedrock would have also penetrated beneath the surface, right? Just makes sense, as is the case with well-known examples of limestone terrains all over the world, which are honeycombed with extensive cave networks and prominent karstification. So perhaps it's not improbable that there could be substantial voids below the surface of the Giza Plateau, as was asserted by author and researcher Andrew Collins in his 2009 book, Beneath the Pyramids, where he actually goes in and explores some caves, not on, of course, on the scale that we're talking about here with this new research, but significant caves nonetheless. But it is a considerable leap to go from natural cave systems to the existence of some kind of massive underground machinery complex or whatever it is that the animations are showing. So for the time being, I'm not going to go beyond that. But I've just been informed that those Italian scientists who published this work are going to be at the Cosmic Summit. So I'll try to keep an open mind.
It'll be interesting. But yeah, the Tomb of the Birds, which Andrew Collins explored, is 500 something yards away from the Khafre Pyramid. And those are karst caves.
Karst caves, yeah.
To your point, the cenotes in Mexico, near Chichen Itza, you have plenty of karst caves underneath those pyramids. So it's not to say that one way or the other, this is disquiet or upsetting these Italian scientists' apple cart. It's just, there's definitely a potential natural explanation.
That's the whole point here. I think there's a potential natural explanation. I would think the natural explanation is, is that it's karstification. So the cave of Hua Fatia in Libya. It's the largest cave in the Mediterranean basin and one of the largest caves in the world, right there. Fatia remains one of the best evidences that humans have existed continuously in one site in Libya. Now, I don't know why that is. But yeah, that's a pretty substantial hole in the ground.
And not that far away.
Not that far away.
Speaking.
Right. Geographically speaking,
Mm-hmm.
it's not that far away at all. Right. So, so we're going to leave it at that, and I'm going to conjecture that there could be large caves. Now, the last question we'll raise then is if these are caves, larger caves, have they ever been accessed by people? And if so, I mean, look, we've seen some of the scale of the engineering capabilities of ancient people on a monumental scale. So it wouldn't necessarily be completely out of the question that if humans had accessed large caves by one means or another, that they could have modified those caves. I think we actually could cite actual evidence that in some cases people did modify caves. On the scale that we're seeing here, I don't know. It remains to be seen.
Well, that is the Tomb of the Birds, right? 5 football fields away. It's caves. To your point, karstification exploited and used by the ancient people for tomb. So it's definitely been done before.
So shout out for Andrew Collins' book. I haven't read it, but now I better go back and read it before the summit. I don't think he's going to be there. Maybe he is going to be there.
It's big in the UK, in the Megalithomania UK group. So maybe we should get you two together.
Yeah, I've seen some of their stuff online, but I've not had any interaction with that group.
Yeah.
Okay, well, I think that's about all my voice is going to, I've been a little hoarse this week, getting better. Another day or two, I should be back to normal, but I don't want to overtax my voice after I've been hoarse. There was something going around. I had 2 days of a sore throat, which is gone, thank God. Hadn't had a sore throat in a few years. Anyways, so at that point, there's always more we could talk about, but we'll save that for another episode. Well, John, thanks for joining me.
Thanks for having me.
And yeah, we'll do this again soon.
Yes, sir. See you soon.
See ya.